All right, I'm going to go ahead and get started. Thank you so much for joining us for this morning's webinar presented by the Clean Energy Solutions Center and the 21st Century Power Partnership, which are both initiatives of the Clean Energy Ministerial. This webinar is on resource adequacy and flexibility, keeping the lights on, and I'm really excited. We've got a great lineup today. Just a few things before we get started. This webinar is being recorded and will be shared with you once the session is over. You will be automatically muted upon joining in throughout the webinar, so please use the chat feature at the bottom of your toolbar to share comments and input. To ask questions to be addressed from the Q&A or during the Q&A session, please use the Q&A function at the bottom of your toolbar as seen here. If you have any technical issues, please use the chat feature to message me, Holly Darrow, and I will help you. You can adjust your audio through the audio settings. If you're having issues, you can also dial in and listen by phone, and that information can be found in your registration email. And finally, we'll be launching a survey after this event ends, and we would appreciate if you fill it out because we appreciate your feedback. So with that, I'm going to hand it over to Dr. Doug Arendt to introduce this morning's webinar and our speakers.
Yes, thank you, Holly, and welcome everyone. It's a pleasure to help kick off this webinar. If we could have the next slide, please. This webinar is part of a series of webinars that are being conducted in collaboration with the Clean Energy Solutions Center, the Clean Energy Ministerial, other activities which are affiliated with power systems. And they build off a body of work that began with collaboration among the power system work streams last year. And there is an affiliated report for that as well that we will put in the chat for the webinar. But for today's session, we wanted to focus in on a quick overview of the Solutions Center, an overview of the Power Partnership. We will then spend the bulk of the technical time on resource adequacy and decarbonizing power systems, and then ensuring flexibility in conventional power plants to integrate renewables, all topics that have been published on over many years, but knowledge continues to advance quite substantially, and we're pleased to bring a number of folks to share their expertise with you on this. And then we'll have an open Q&A session at the end that I'll be happy to moderate. To work us through the topics today, if you could go to the next slide, please. You'll see that I'm joined by 4 other experts. Soon we'll hear from Rob Horner, who's in international relations at the U.S. Department of Energy, Jeff Logan, who has been a colleague and partner in the 21st Century Power Partnership for a considerable amount of time. And then 2 technical talks, one by Gord Stephen, who's a systems research engineer at NREL, the National Renewable Energy Lab, and a second talk by Priyam Jain, who's the manager at Grid Controller of India. So with that brief introduction, I'll turn it to Rob for a bit of an overview of the Solutions Center. Thank you.
Thanks, Doug. Hi, everyone. Good morning, good afternoon, good evening. Thanks for joining us today for our webinar. My name is Rob Horner. I'm with the U.S. Department of Energy, and I'm here representing the Clean Energy Solutions Center. As you heard earlier, the Clean Energy Solutions Center is part of an initiative of the Clean Energy Ministerial. It's led by Australia and the United States and operated by the National Renewable Energy Laboratory. Our objective at the Clean Energy Solutions Center is to accelerate the transition of clean energy markets and technologies with a primary focus on supporting governments in the developing world. The rationale is that many developing governments lack the full access to all of the resources that many developing world governments do in accelerating the clean energy transition. And we're here to provide some of that technical expertise to help them in their own transitions. Next slide, please. So the Clean Energy Solutions Center accomplishes this through 3 primary activities. I think our flagship activity is the Ask an Expert service. If you go to the Clean Energy Solutions Center website, which you can find on the Clean Energy Ministerial's website, there is an easy way for governments in the developing world to ask technical questions, technical policy questions about their clean energy transitions. We will answer those questions free of charge using our network of clean energy policy experts. We also have a lot of training capacity building, including the webinar that you're listening to today. We have a series of webinars and a library of those recordings on our website. We also have a resource library. In addition to the webinars, we have reports, policy briefs, journal articles, etc. So I won't belabor this. I'll get us straight to the meat of our presentation, but thank you for joining us this morning. And I think I'll hand it back to Doug to go over the 21st Century Power Partnership.
Hi, good morning and good afternoon and good evening, everyone. I'm Jeff Logan. I've been working with Doug and some other colleagues for quite a few years, helping to run the 21st Century Power Partnership, which is one of the initiatives of the Clean Energy Ministerial that focuses on power transformation. And if I could have the next slide, please. 21st Century Power Partnership has been around since I think 2012. And what our objective is in the 21 CPP is to help countries transition not just using renewables, but the entire system-wide transformation that's required to make power systems cleaner, more reliable, and more affordable. So you can see here what the overall objective is of the 21 CPP. And again, like Rob, I will try to keep this as short as possible so that we can get into the meat of the presentation that Gord and Priyam are going to provide today. So if I could have the next slide, please. Our annual program of work focuses on what we call thought leadership studies and providing technical assistance, either on a bilateral or sometimes regional basis to other countries to help them focus on the specific challenges they're facing as they transition their power sectors. And we also provide information exchange, capacity building, and on occasion fellowship programs where people can help to build capacity in their technical capabilities. And the next slide. This is just a quick snapshot of some of the reports that we have produced over the years. We have quite a database of thought leadership reports on our website. And Doug mentioned a report that today's webinar is based on, and that's highlighted here in the middle: lessons learned for rapid decarbonization of power sectors. And I put a link to that in the chat of today's webinar for people who are interested in learning more about that. And the next slide, we're going to take a quick look at a short video, which is now quite old, I could say. And it is a video that shows the results of a grid integration study that the 21st Century Power Partnership and many other organizations produced back in, I think it was 2017. And the video shows how over the course of a day or 2 days, the generation of, right here you can see the shade going across India in the morning, and that's signaling daylight, and the emergence of a large amount of solar generation that comes online in the year. It's a futuristic study where it looks at the build out of new generation over time, and the study really focuses on whether or not the grid can be operated reliably given the growing amounts of variable renewable energy. And what happens to, and Holly, if you could click the forward arrow again, just to keep it running. It shows how the grid is operated and how plants need to be ramped down or ramped up depending on how much solar is available, and wind as well. But in this case, we're going to learn much more about this in the second presentation today that Priyam Jain provides. I just wanted to give a very quick snapshot of that. This really illustrates the challenge of providing flexibility in operating your grid when you have large amounts of variable renewables and other options available. So the next slide is just a transition to our first presentation today that Gord Stefan will offer on resource adequacy. With that, I'll stop. Thank you.
Great. Thanks, Jeff. And I will share my screen. Folks are seeing that okay?
Yep, looks great.
Perfect. Okay. Thanks. Yeah, so hi everyone. My name is Gord Stephen. I'm a research engineer at NREL here in the United States. I work a lot on resource adequacy topics, and at NREL we actually have an open source resource adequacy tool that I lead the development of. So if folks are interested in some resources about that, feel free to reach out to me. Today, I'm happy to be with everyone to talk about this topic of resource adequacy in decarbonizing power systems. This is a topic that maybe unsurprisingly has gotten a lot of interest in the past few years as we move towards more decarbonized power systems with more variable resources like wind and solar on the system, and how do we make sure that we're keeping those systems resource adequate. In particular, I've been a part of a task force under the Energy Systems Integration Group called the Redefining Resource Adequacy Task Force. And we've put out a number of publications on this topic over the past few years. So in particular, today I'm going to draw a few points from two of these publications. The first being the original Redefining Resource Adequacy for Modern Power Systems report that we put out a few years ago now. And then a little bit after that, we also put out a second report on the intersection of resource adequacy and public policy, which we put out for the COP26 climate conference. So I'm going to draw on a few points from both of these works today in the time we have together, but I would definitely encourage folks, if what they hear is of interest or they want to dive deeper into these topics, you can access both of these reports at the link there on the slide. And I think Holly's going to drop the link in the chat as well at some point, so folks can click through and access those there. And then at the end of the presentation, I'll also mention a couple other references that I think may be of interest to some folks. So as for a starting point, it's probably best to lay the groundwork, make sure we're all on the same page in terms of what is actually resource adequacy. What do we mean when we're saying that? And how does that relate to other aspects of power system performance that we care about? So there's lots of different things that you would want out of a power system in terms of designing one and in a future power system that meets different expectations of society. As Jeff alluded to earlier, obviously we want it to be affordable. We want it to be sustainable and in line with decarbonization goals. And we also want it to be reliable. And within the kind of umbrella of reliability, we have a number of different aspects of power system reliability. And I would argue that resource adequacy is the most foundational of all of those aspects. Resource adequacy, I think this is a good quote from an EPRI report, the way they describe it as assessing whether a power system has an appropriate set of resources to maintain continuous service to demand with a desired level of certainty. So it's really about the fundamental supply-demand balance on the power system. Do you have enough electricity available, and are you able to move it to the right places to serve demand everywhere all the time? And of course, we know that that's not physically possible to have 100% certainty that you can always serve load everywhere, because there's always going to be events happening that could compromise that capability. But we want to assure that we can do that with a sufficiently high level of confidence, or in other words, there's a sufficiently low level of risk of having some kind of shortfall event. And once we have that kind of basic supply demand balance, and we've determined that we consider our system resource adequate, then we can think about these other kind of more technical aspects of system reliability in terms of transmission stability, the reliability of the distribution system, flexibility in reserve products, and resilience to extreme events. But resource adequacy kind of lays the foundation for all of these things. So then the next logical question might be, do we need to change how we think about resource adequacy? I mean, this is a topic that we've been studying as long as there have been power systems. But under the transition that we're experiencing now in power systems around the world, there really are some things that change some of the underlying assumptions that go into trying to assess whether or not a particular system would be considered resource adequate or not. Especially historically, this type of analysis has really been focused on risks arising from thermal generating plants. So if you have a coal plant, there's some probability that at any given point in time, there's some mechanical issue or failure that happens with that plant that forces the generating unit to be taken offline for repair. And while that unit's offline, obviously it's not able to produce electricity and contribute to that supply-demand balance that we talked about previously. And if you get unlucky enough and enough of these kind of random failures happen all at the same time, you can end up in a situation where your ability to balance supply with demand is compromised because of a lack of supply. So traditional resource adequacy analysis has really focused on trying to quantify the probability that you end up in that kind of unlucky situation where you have a bunch of these independent failures all occurring at the same time. But in decarbonizing power systems, what we're seeing more and more of is the risk of a supply shortfall is moving away from that kind of thermal generation driven risk and towards weather driven risk. As we integrate more and more renewables into the system, what's going on with the weather in terms of whether the sun is shining and whether the wind is blowing becomes an increasingly important factor in overall levels of system adequacy. And what's more, we're also seeing increasing integration of energy limited resources. So that's things like storage or potentially load flexibility that may be able to provide resource to the system at a certain point in time, but that ability to do that is dependent on intertemporal coupling between what's happened in the past. So for a battery, for example, that battery needs to charge up at some point to be able to discharge later on. So we see this chronological coupling where we have these dependencies across time where what happened on the system yesterday or 12 hours ago may be impacting your ability to serve electricity right now. And then this is compounded by this idea of correlation between all of these different factors that wasn't as prominent historically. So I mentioned when we talk about thermal generating plants, we very frequently think of the availability of any one thermal generating plant as statistically independent from the rest of the fleet. So some random component failure at one facility isn't necessarily going to be driven by or cause issues at other facilities. When we start thinking about variable renewable energy and weather-driven impacts, this assumption has to change. Obviously, if the wind stops blowing in one place, that may also mean it stops blowing nearby in other locations, and we lose all of that wind generation at once. So we have a much higher correlation in the availability of these different resources. So because of all of these considerations, which are in some cases totally different from the historical way that we've thought about resource adequacy and assessed it, That resource adequacy task force that I mentioned earlier proposed 6 fundamental principles of resource adequacy analysis that address these emerging issues. I'm only going to speak to 4 of them today, just for the sake of time, but I'm happy to talk through all 6 of these or talk about questions on all 6 during the Q&A session. So in particular, I'm going to talk through these 4 principles here in the next 10 minutes or so. So I'm going to start with principle 6. Which is actually the last principle, but in some ways I think it's the most foundational of them when it comes to deciding how we want to design a system. And that's the question of choosing our resource adequacy criteria, basically deciding how much resource adequacy we actually want from our power system. Like I mentioned earlier, we can't get to 100%. That's not technically possible. But we can, depending on our preferences, spend a lot of money to get really close to 100% or not. And that choice really comes down to a balance between the benefits and the costs of that additional reliability. And in a lot of places, historically, we've kind of thought about resource adequacy criteria as this fixed engineering principle that we need to achieve. And the point we wanted to make with including this principle in the report is that resource adequacy criteria shouldn't exist in a vacuum. It's all about policy and economic trade-offs between the benefits to society that are delivered by having increased resource adequacy and the costs that society would have to incur in order to achieve those benefits. So as you develop, or as you choose a resource adequacy standard, and you do these probabilistic studies and quantify the probability of having a shortfall, as you increase the stringent nature of that criteria and expect a more and more reliable system, it's important to keep in mind that that comes with an implicit cost of doing that and an implicit valuation of what the opportunity cost to society is of failing to supply all that load. So as your criteria becomes tighter and kind of higher performance, you're valuing your lost load higher and higher in doing so. And it's important to keep to strike the right balance between those 2 factors. The next principle has to do with chronology and studying multiple weather years. So this relates to what I talked about earlier about the need for understanding the temporal relationship between availability of different resources. Historically, what we would do is just think about what's the peak demand that the system is going to be expected to serve. And as long as I build enough generation to be able to serve that peak demand, and then I add in a bit of buffer on top of that for accounting for the fact that maybe load will be a bit higher than I expect, maybe some of those generating units will be offline and not able to generate. As long as I build in that buffer during that peak demand period, that kind of most stressful time of the year, then I'll be okay the rest of the year as well, because serving less demand than that is always going to be easier. What we see as we start to integrate more renewables into the system is those assumptions no longer work. It's not just about when your demand is high, but it's also about when your renewable availability is low that causes these stress conditions. And it's hard to know in advance without actually looking at every hour of the year or of whatever the simulation horizon is that you're using to test whether your system is going to be adequate or not. You need to look through all those different hours to find those times when you have these shortfall conditions. And the particular mix of wind generation being low versus solar generation being low versus demand being high, the particular balance between all of those that leads to your riskiest conditions really are very dependent on the specific nature of the individual system. So you kind of need to do this hourly analysis to find out when that risk happens. And because of all the weather-driven impacts that I talked about earlier, we also not just need to study every hour of 1 year, but we really want to grab as much data as we can get about weather conditions and situations that you could expect to find the grid in, so that you can develop an accurate understanding of what the probabilistic risk of being in a shortfall condition is based on as many years as weather data as possible, or as much information as you can gather about the relative probabilities of different types of weather scenarios being experienced in the future. And in particular, as we move to higher and higher levels of renewables, we can expect an even stronger decoupling between times of peak demand and times of peak system risk. In particular, what we start to see as we look out to futures is systems that maybe historically always had their highest risk in the summer when it was, say, very hot and there was a lot of air conditioning load. It's something we see a lot here in the United States. That drives up demand and causes those peak kind of summer risk hours. What we're starting to see now is more and more solar comes onto the system. That peak demand period is often correlated with lots of solar generation, and the actual risk to the system is relatively low. And the highest risk periods to the system may actually shift to a different season altogether. It may be that in the winter, when it's darker, and maybe there's a multi-day wind lull. Those are kind of the scariest conditions that the system encounters. And identifying how often those types of situations occur and what those actually look like require this chronological modeling and this multi-year data set of all these different weather conditions to understand how acute that risk might be. The next principle that I'll talk about, we're kind of going not in numerical order here, has to do with identifying the specific risk characteristics that your system is faced with. And that can be in terms of the frequency of events, the duration of events, the magnitude of events, so how much shortfall you encounter when you're in a resource adequacy deficit, as well as the timing of those events. So when, in terms of time of year and time of day, those events are happening. So this figure here is from the Mid-Continent Independent System Operator in the US. The blue line you see at the top here is their sort of original current day load profile. And you can see the peak load sort of occurs at this point. That's when the most risk is on the system. Like I mentioned before, as we shift to a system with higher levels of renewables and in particular higher levels of solar PV, this risk actually shifts away from this peak period into later in the day, into the evening, where demand is still relatively high, although it's come down slightly from its peak. But the sun is now setting, and all that solar generation that we were able to depend on earlier in the day is no longer available. So what you see here with the different colors is as you add more solar onto the system, the net load, basically the total load of the system minus that renewable generation, is actually very low during these peak demand periods because there's lots of solar generating. But then it spikes up in the evening as that solar goes away, and so the net load actually increases even though the absolute load is going down. And what we see is a concentration, sort of a compression of the risk from this kind of diffuse risk where there was elevated risk all afternoon. We now see it being compressed into the hours around sunset and just after, where the risk actually is higher in those periods, even though the demand might, or the net demand is lower. And this has really important implications for the mitigation strategies we choose for how to improve resource adequacy if we feel that we're in a shortfall of it. When we kind of have this more diffuse risk over longer periods of time, we need resources that can provide extra power over that full period of time. And so in a traditional kind of historical context, we would typically think of investing in a new thermal plant, like a new combustion turbine peaking plant, as the right solution to address that shortfall risk. But as we move to these periods with this compressed risk into a smaller number of periods that are immediately after a time of large surplus of energy on the system, other technologies like storage start to look much more attractive as the least cost solution for addressing these risks, just based on the specific nature of the event and the shortfall and when it happens and how that relates to the chronological nature of production. That resource starts to become a lot more attractive. That storage can charge up in the afternoon, and then it only needs to just charge for a couple hours to get you through that risk period before you're at a point where risk is reduced back to low levels or negligible. But understanding how this relationship works between the specific risks you need to address and the mitigation strategies or investments you can choose to make to account for that really does require this kind of more detailed understanding of the timing, the duration, the magnitude, and the frequency of individual events that you see when you're studying these future systems. And finally, I'll briefly touch on principle 3, which has to do with the fact that there is no such thing as perfect capacity. So I mentioned historically, oftentimes we would think of thermal peaking plants as the solution for improving resource adequacy. You know, these are relatively low capital costs. They may have higher operating costs, but because we're only using them for short periods of time when we have these deficit conditions, that kind of economically made sense. But even these resources aren't immune to unavailability issues. And in particular, what we've kind of come to understand more clearly in the past few years is that there's lots of other kind of types of risk associated with those types of units that we need to be accounting for when we're deciding how resource adequate we want our system to be and which resource mix is required to get to there. So in particular here in the US, there have been plenty of examples of situations where times of highest system stress have also aligned with times of low availability from resources that we've historically thought of as kind of always being there and being super dependent. So things like cold waves that drive increased outages in the thermal generation fleet are kind of classical examples that we've come to understand as situations where even these kind of so-called, firm resources like a combustion turbine, they're not perfect, right? There's some increased risk that they're not during times of need, and we need to make sure we're capturing that in our resource adequacy assessment and in our investment plans when deciding where are the appropriate resources to design an overall resource adequate system. So as I mentioned, all of this content, those 4 principles I talked about, plus another 2, can be found in more detail in these reports with the link there at the bottom. That'll take you to a page that has both of those reports, plus additional fact sheets and summaries for that kind of wrap up all this information into more digestible formats as well. And I'd highly recommend both of those if folks are interested in learning more about resource adequacy in decarbonized systems. A few other resources I would also recommend if folks are interested in the issue of choosing the right risk metrics, so how you actually measure the reliability or the resource adequacy of your power system, and what a particular criteria for resource adequacy should be using one of those metrics. 2 reports I would recommend are this one from EPRI, which I mentioned at the beginning of the talk. It provides a really nice reference overview of different types of risk metrics. This is a paper we published or presented at CGRE last year as well, which goes into kind of a more forward-looking thought of how resource adequacy metrics may need to change in the future. And finally, folks are interested in capacity accreditation, kind of this idea of how we can convert variable resources or energy limited resources into a more traditional firm capacity contribution that we can use in a planning reserve margin context. We just this winter put out a paper on that topic as well. This is just some extra detail from that EPRI report, which I thought was kind of interesting. So like I mentioned, they have that kind of reference table looking at how different metrics are defined and how they, the kind of the strengths and weaknesses of when you might want to use them. They also have this table at the back that I found very interesting that lists lots of different countries and regions across the world and what specific resource adequacy metrics they're using as of today, or when this report was written, and the specific criteria or like the numerical thresholds of those metrics. So if folks are interested in learning about what different places are doing, that's a useful resource to look at as well. And links to all of those reports and documents are included in the presentation. Thank you. So I will wrap up there and hand it over to the next speaker.
Holly, we have a couple of specific questions for Gord now. Should we do them now or should we hold them to the end?
We can hold them to the end.
All right. Priyam, please, the floor is yours.
Yeah, thank you. Can someone confirm whether my screen is visible and whether I am audible?
Yeah.
Looks good.
Okay, thank you. Yeah, Hi everyone. I am Priyam Jain. I am currently working as Manager System Studies at National Load Dispatch Center of Grid Controller of India Limited. Today, I will be covering the role of flexibilization of conventional power plants to facilitate large-scale renewable integration. And I will be taking the example of the Indian power system for the same. So, today's presentation would cover the following in sequence. First, I will be covering the overview of Indian power system, including the current generation and capacity mix, the future roadmap for renewable integration or the clean energy transition in Indian power system. Then I will be covering the requirement for increased flexibility, both with the increasing variability on the demand side, as well as for facilitating the large scale renewable addition. Then what are the major flexibility service providers, both on the generation side and the demand side, and the role of coal-fired or the thermal generators in providing the requisite flexibility, and what are the key initiatives that have already been taken in the Indian power system to facilitate the same. So, coming to the Indian power system, it is one of the largest synchronous grids in the world, with an installed capacity of around 417 gigawatts. The current peak demand met is of the order of 220 gigawatts, which has been met recently in the month of May itself. And the current installed capacity of renewables, including large hydro, is 172 gigawatts. And the installed capacity of solar and wind generation sources stands at around 110 gigawatts currently. So the clean energy transition in India has already started, and same is also getting reflected in the annual and daily VRE penetration, and as well as in the maximum VRE penetration. So we can see that the annual wind and solar penetration in energy terms has already touched around 11% in the last financial year, whereas the maximum VRE penetration in maximum daily VRE penetration is almost double of that at around 21%, whereas the maximum instantaneous VRE penetration has been recorded as 32% so far. And some of the RE-rich states, such as Karnataka, they have already touched the maximum instantaneous VRE penetration of more than 100%. And that implies that they have met all of the demand through renewable generation sources only. So the clean energy transition roadmap in Indian power system has already been notified by the government of India. And as per the roadmap, India will integrate 500 gigawatts of renewable energy, non-fossil capacity by 2030. And most of that non-fossil capacity will come from solar and wind generation sources, with both of these combined contributing to around 400 gigawatts of that non-fossil capacity. Accordingly, the mix of solar and wind generation in 2030 would be around 51%, and these two will be the two major sources of the total capacity mix, replacing coal as the most dominant source at present. So then, in order to facilitate this large scale of renewable generation in near future, there is requirement of additional flexible resources in the system. But renewables are not the only reason for this increased demand for requirement for flexibility. So there has been an increasing trend in variability on demand side also. So here we can see the demand trend for the month of February, which usually is the winter period in India. So here we can see the steep ramp in the morning demand during the morning demand hours, And the typical ramp rate is of the order of 250 megawatts per minute, with the same increasing to around 500 megawatts per minute on some special days. As I mentioned earlier, the main reason for this increasing variability on the demand side is not only the integration of renewables, but also the disproportionate increase in minimum and maximum demand. So here we can see that the difference between the maximum and minimum demand during the last 10 years, it has increased significantly. And now we see the daily load variations of the order of 70 gigawatts. And this has increased the requirement of flexibility on the generation side also, which has been met through additional flexing of the thermal fleet and the hydro generation. Now, because of the integration of renewables also, the requirement of flexibility has increased significantly. So the curve here shows the all India demand and the all India net demand and the thermal generation trend for a typical day. So here we can see that thermal generation of around 140 gigawatts watt was on par on that particular day. And the technical minimum level comes out to be around 88 gigawatts, considering the average of 55% and 70% technical minimum level is specified for the central and state generating units respectively in the Indian power system. So here we can see the increasing duck curve valley and the significant difference between the all India demand and all India net demand during the peak solar generation period. And accordingly, to accommodate the same, the thermal generation has been backed down. Now, this curve also highlights that if in near future, when more solar generation will get added, there will come the requirement when we will have to reduce this technical minimum or minimum power level criteria of the thermal fleet available, or to accommodate that additional RE generation. So definitely the curve value is increasing and it requires more flexible generation resources in the system to accommodate the same. Now, what all are the major flexibility providers in any power system? So gas and hydro-based generation are the most flexible resources, and they have been providing the necessary flexibility in Indian power system also, as can be seen from the gas generation trend for a typical day, where the peaking capability is being provided by the gas generation. However, at the same time, we can see that the trend of gas generation has been on a declining trend because of the availability of domestic gas and the high gas prices globally. And therefore, the flexibility provided by the gas generation sources is constrained by the availability of domestic gas. So the same cannot be relied on for facilitating the large scale renewable generation as of now. Similarly, hydro has also been the most effective flexibility provider so far in the Indian power system. And you can see that the scheduling of hydro is carried out in such a way that it provides the necessary peaking capability during the morning and evening peak demand hours. However, the flexibility provided by the hydro generation sources is also, as the hydro generation is quite seasonal, the run-of-the-river plants, the flexibility provided by them depends on the hydro inflows. Because of this seasonality, the flexibility provided by hydro generation is also quite very seasonal. It is highly seasonal. So the responsibility of providing the necessary flexibility then comes on the coal-fired generation, which also is the major source of generation in Indian power system. And it has been providing the necessary flexibility over the years, as can be seen that the hourly ramp of the all India thermal generation has increased quite significantly during the last 10 years. Now, along with harnessing the flexibility from the generation sources, the load side flexibility is also being harnessed. So this curve here shows the time of occurrence of maximum and minimum demand in Indian power system over the last 12 years. So historically, we can see that the maximum demand used to occur during evening peak hours. And now, during the recent years, the occurrence of maximum demand has shifted to afternoon hours due to the availability of the cheaper solar generation during this period. And this has been uh, uh, made effective through catering of the agricultural loads from shifting of the agricultural loads from the evening peak demand hours to the afternoon hours. Now, this has, in a way, provided the requisite flexibility to some extent by reducing the quantum of thermal generation that needs to be back down during the afternoon hours. And secondly, by shifting the by shifting some of the evening peak demand to afternoon hours, therefore reducing the ramping requirement during the non-solar hours. So, as the flexibility provided by the gas and hydro generation sources is highly dependent on the availability of domestic gas and the seasonality. So, thermal generation has a huge role to play in integration of renewables in Indian power system. Here we can see that it is the major source of generation at present, contributing to around 71% of the total annual generation. However, it also projected to remain a major source of generation in 2030 also. It will contribute to around 55% of the total annual generation in that year, though there will be a huge capacity addition of solar and wind generation sources in that time frame. But still, it will be one of the most dominant generation source, and therefore it is imperative that the flexibility provided by the huge thermal fleet at that time is properly harnessed. So, optimal generation capacity mix studies have been carried out for the year 2930, and the studies have brought out the optimal capacity as well as the generation dispatch for that particular year. And it has been observed that during the maximum RE penetration day, the maximum VRE day, the system is not able to absorb the full RE capacity, and there is curtailment expected of the order of around 1.2%. And this is considering the technical minimum level of the thermal fleet as 55%. However, if we reduce the same to 40%, then this curtailment during the maximum VRE day reduces significantly. Similar exercise has also been carried out for the whole year, where we can see the percentage VRE absorption for the whole year. And we can see that the RE absorption is likely to decrease to as low as 95% on some of the high RE days. And this also is because of the inflexibility constraint posed by the thermal generators. And we can see that the total RE curtailment is of the order of 0.78%, considering the minimum power level of thermal fleet as 55%. However, if we reduce the same to 40%, the curtailment reduces to 0.25% from 0.78%. So there are significant benefits of by deriving the flexibility of the thermal generators, and various key initiatives have already been taken in this regard. The importance of the flexibility that can be provided by the coal-fired units has been duly recognized by the regulators and policymakers. So the first major initiative was way back in brought down the reduction of brought down the technical minimum level from 70% to 55% for all central generating stations. And it also incentivized the operation of thermal plants at lower operational levels by providing compensation for increase in the heat rate at lower operational levels, the increase in auxiliary energy consumption of thermal power plants at lower operational levels, and by providing compensation for start of fuel cost for over and above 7 start stops in a particular year. Then in 2019, in the terms and condition of tariff regulations for thermal plants, the ramping capability beyond the threshold of 1% was incentivized by providing 0.25% additional return on equity for every 1% increase in the ramping capability, and similar provision for penalizing through return of equity was also brought out in case of failure to provide the specified 1% ramp limit. Recently, in 2023, the Central Electricity Authority has brought out a key regulation on flexible operation of coal-based thermal power plants, and the regulation specifies that the minimum power level of all thermal generating units shall be 40%. All the units shall be capable of operating at the minimum power level of 40%. This is for new units as well as for old units also. And for implementation of the same for older units, the phasing plan has also been prepared. And all the thermal power units will be able to operate at this minimum power level by 2030. And similarly, all the thermal generators have been mandated to provide a ramping capability in the range of 1 to 3%. So, as I mentioned, a draft phasing plan for implementation of this 40% technical minimum level has been prepared. And in the first phase, the first phase will start from July 2024. And before that, a pilot phase will be conducted where already 11 units of central, state, and private sector have been selected. So this pilot phase will be implemented in 6 months, and the learnings of the same will be compiled, and these will be used in the next 6 months, and these will be useful for the subsequent phases. Then the first phase will start from July 2024, and in the period of next 2 years, all the units commissioned between January 2016 to December 22, the capacity comes to around 56 gigawatts. These will be considered for the implementation of the necessary measures for achieving this 40% technical minimum level. Similarly, in second phase, the capacity of around 53 gigawatts will be taken up. Then subsequently, in phase 3, capacity of around 25 gigawatts. And in the last phase, capacity of around 58 gigawatts would be taken up. And so this is the phasing plan for implementation of this 40% technical minimum level to around 200 gigawatts of coal-fired capacity present in Indian power system currently. So the major action points for harnessing the flexibility from the thermal fleet could be the timely implementation of this 40% technical minimum level as per the phasing plan. Then incentivizing the generators for the incremental cost that come because of the operation of the thermal units at low loads. Then there is also requirement for exploring the possibility of 2-shift operation of the existing thermal units. The various pilot projects on the same are already going on in India, but an action plan to implement the same across the whole thermal fleet needs to be prepared and implemented. And lastly, the capacity building and knowledge dissemination across all the power sector stakeholders needs to be carried out, because at present there is the utilities and the generating stations are quite reluctant regarding the operation of the thermal units at low load levels. So this is also one area that needs to be emphasized in near future for the flexibilization of thermal units. So yeah, that's it from my side. Thank you. Thank you.
Yeah, that's wonderful. Thank you, Priyam and Gord for fantastic presentations. We do have a few questions, and Priyam, if I may call to you since you just finished, and then we'll go back to Gordon. There's another one as well on the Solution Center. The last point that you just made in terms of knowledge buildup of the operators and the executives over those coal plants, I think is quite pertinent, and it's reflected in perhaps the phasing, and I think the rationale in your phasing reflects the age of those plants and their ability to ramp, and so you give the older ones more time to prepare for that change in operations and other elements. And so is there experience in India which is developing that shows that there are new lessons to be shared regarding how to either modify a plant if it needs to be technically modified, or how to operate it differently in order to be more flexible? And I asked this question in context of I believe the coal flexibility report that was released back maybe in 2015 that did reflect on experience from Denmark as well, which I believe you and colleagues are quite familiar with, which showed up to 95% ramping. And so you're incrementally moving in that direction, and would love to just get some of your experience if you could share that with us.
Yeah, so first, regarding the retrofittings and the other necessary measures, like the tuning of the control systems that are required for achieving achieving the operation at lower load levels. So various pilot projects have already been done in Indian power system, and I think most of the generating companies are now familiar with the issues that come up that arise because of the operation of the units at lower levels. However, during operations also there are various aspects that need to be taken care of. So I think from that aspect, the operator that would be operating that plant in real time. So the operator needs to be made aware of all these aspects, that what are the issues that may arise in real time because of the operation of these units at these low load levels. So I think this is one area where currently the necessary training and knowledge dissemination needs to be focused on, because all the necessary measures to achieve that low load level that are already taking place. So, but in real time, there are various issues that arise. So I think that is one area where the focus should be now, which as the phasing plan has already come up.
I think you're muted, Doug.